Bismillahirrahmanirrahim. Good evening, guys. Let me start to explain this experiment. I'm talking about how we can determine, how we can calculate the focal length. That means I'm talking about the focal length distance of specifically convex lens. Let me go to my PowerPoint. Yes, this one. The focal length of convex lens experiment. Let me talk about the theoretical important things at first. Our purpose to determine the focal length of a specific convex lens. Let's can be like this eyeglass or the dental tool when do some diagnosis procedure to any patient. We can use this picture. For example, let's try to determine the focal length to this convex lens or to this eyeglass. Okay, let me start from here. Concave lens is a converging lens. What that mean? That's mean at some point, this point is the focal point. All the light rays refracted will converge at this point, like this picture will illustrate to us. The focal length is the distance between the focal point and the center of this lens. Here, it's clear. All of these are parallel light rays. After through from this convex lens, all of these parallel rays are refracted to converge at this point. This point is a focal point. And this point, this point position will change from convex lens to another. That's specifically according to what we need from this lens to make an eyeglass. That's depending on the patient defect, or to use like the situation, to use it as a diagnosis procedure, to give opportunity to the dental to take a look to something. This slide is finished. Let's talk about the uses of convex lens. Actually, at microscope, camera, and to magnifying glass to produce a larger image to any object, used to correct long side defects, like this previous lecture, previous slide, when I was talking about the glass eyes. Okay, now our working will be depending on this experiment. We have a light source, the object. Actually, the object can't make a picture, can make a refraction picture at this screen without light source, because it's necessary. We will turn it on to make a light rays. Some of these light rays will through from the object, and after that from the convex lens to make our picture here at the screen. That means, let me focus on the important things. The first thing is this ruler. This is important. Our distance will be, for example, let's say 90 centimeters. That's mean 90 centimeters. That's mean from the distance between the screen and the object must be 20 centimeters. No more, no less. And after that, we will leave these two positions and work on the lens. Let's make it go on, or let's move its position to can achieve a clear picture here, a clear image. After that, we will calculate U and V. What does mean U? What does mean V? V, that's mean the distance between the screen and the lens. And after that, we will calculate U to be the distance between lens and the object. All of them, collect all of them, that mean will be equal the distance between the screen and the object. Now, let's talk about this function, this equation, sorry, it's important to can calculate the focal length to any convex lens. It's equal reverse focal length equal reverse the distance between object and the lens plus reverse the result of distance between screen and lens. But we can simplify this function by using this simple math trick to make it the focal length, avoiding reverse anything, avoiding adding any columns more. Function will be the focal length will be u multiple v divided on u plus v. This is very important. It illustrates to us how the screen, how the image will be opposite at the screen. Let me explain that. Here is the object, and after it, sure, we have the light source to make this, to generate these light rays. And here I have my convex lens. The convex lens has two faces, from right equal the left, okay, because that we have two focal lengths, and the focal length will be a constant to any, let me change the words, let me say any convex lens has constant focal point, that means constant focal distance. By that, when I say, for example, the focal length here is 10 centimeters, that means 10 centimeters from left and the same distance from left, okay? Let me come back to the objects. By the light source, we have many light rays. One of them will be reflected like that, throwing from the focal length, number two. And first one is refracted actually, and will take the parallel side, the parallel direction after throwing from the convex lens. And from the center will be without any reflecting because it's through from center of this lens. By that, I will have inverse picture. That's mean when I have a tree at this object, that's mean I will have inverse tree at the screen with the same size. And our duty today at this experiment, we will work on the same distance, but you can change the positions of this object by increasing it or decreasing it, like what's happening in camera when the photographer do some change in the camera to make zoom, for example, to a specific object. He is working on the focal length distance to the same convex lens. Here, I use these two pictures to illustrate the different distances. When I say let's work on 90 centimeters, that means the distance between the object and the screen will be 90 centimeters, and change the position of this convex lens to can manage the U and V distances. Here, let's say it's 50 centimeters, the distance between the object and the screen. Now, let me come back to math side of this experiment. Here, how the question will be in the exam. Determine the focal length of two dental lenses according to the column below by using window method. And don't forget to do a comparison between the results. Here I will give you the distance. You will have U or V. It's the same. You can use the distance because distance equal U plus V. That's mean if you have missing V, you can use the distance value and U value to can manage V value, okay? That will be the distance equal U plus V. By that, V will equal distance minus U to can fill all of this column. U multiple V independently column, U plus V with independently column. Because to can achieve all of these 5 results, when I have 5 results of U and 5 results of V, that means I have 5 results of focal length distance. But the condition is must all of these results must be near from each other to can say our working is right. Here I will use this function when inverse f equal inverse u plus inverse v to can achieve this easy function. Actually, it's easier from the common way. F equal u multiple v plus v multiple u. Now we will calculate the focal length to each u and v values. You can achieve from 4 u and v values, you can achieve 4 values of focal length distance. Okay, and after that, like this, all of these are near from each other. By that, we can say f average equal 12.712 centimeters. Don't forget the units, it's important. Now let's use another way to can know our solution is right or not by using the graphical way. Let's say uv at the y-axis from the function and v plus u at x-axis. By that, slope from the math function equal delta u divided on delta x. That's mean slope here equal delta u multiple uv divided on delta, or yes, delta, it's more appropriate, delta u plus v, like that. That's mean slope equal the function, the focal length distance average. By that, we can collect it, we can manage it directly by using this curve, this graphical way. Here I did a rounding number here when I'm talking about 25.256. I directly I make it to be 950, and the same with the others by using the rounding numbers. Important, you must have enough information about it to avoid any simple mistake can happen. Here at x-axis, I say each 2 centimeters from x equal 10 centimeters of u multiple u plus v. At y-axis, each 1 centimeter equal 100 centimeters of uv. By that, each 1 millimeter equal 10 centimeters of uv. I put it all of these number at their right positions. You can achieve the slope equal 12.33 centimeters. That means I can say the result from using function, focal length distance function, it's near from the result from graphical method or graphical side. Let's say at conclusion, the relation between inverse V, or let's use the easier way. Let's say the relation between u multiple v centimeters at x-axis and u plus v centimeters at y-axis is linear relation. Here it's direct, not inverse, because I used another way, the easier way. That means when one of them increase, the other will increase too. The result by using focal length distance law and from graphical method are near from each other. That means our results are acceptable. Here, but here, be careful because here was talking about another graphical, like the syllabus said and wanted from me, by dealing with 1 of v divided on v and 1 divided on u. But I say let's use the easier way by make the relation be from u multiple v at y-axis and u plus v at x-axis to make the relation be direct, not inverse. Thank you about your watching or listening. Have a good day and see you at next lecture.